Today we will discuss about reciprocal lattice. So before describing the reciprocal lattice, we should know what is the importance of this concept. So you know what is Bragg's diffraction, X-ray diffraction from a crystal structure. When an X-ray is diffracted from a crystal structure, it will produce diffraction peaks corresponding to different planes from the crystal surface. And if we are considering the diffraction surface, it is of three-dimensional or two-dimensional structure. It will be the slope of this structure and the diffraction pattern we will obtain after this diffraction. So in order to simplify this problem, Paul Peter Ewald developed the idea of reciprocal. The idea underlying the development was that each set of parallel planes could be represented by a normal to these length equal to the reciprocal of the interplanar spacing. Thus, the direction of each normal represents the corresponding set of parallel planes, and its length is proportional to the reciprocal of the interplanar spacing. So how this reciprocal lattice comes? The idea was that each set of parallel planes in a crystal structure can be represented by drawing normal to these planes having length equal to reciprocal of the interplanar spacing. So considering two planes, we are choosing an origin and we are drawing with spacing equal to reciprocal of this interplanar spacing. Thus, the direction of each normal represents the orientation of the corresponding set of parallel planes, and its length is proportional to the reciprocal of the spacing. So this is the idea of lattice. Okay, the normals are drawn with reference to an arbitrary origin, and endpoints are marked at their ends. These points from a regular arrangement, which is called a reciprocal lattice. Obviously, each point in a reciprocal lattice is a representative of a parallel set of planes, and it becomes easier to deal with such points than with a set of planes. That is, in the reciprocal lattice idea, what we are doing is we are drawing normal to a set of parallel planes with length equal to the reciprocal of the interplanar spacing by choosing an arbitrary origin. So we will end up with different points corresponding to set of planes. So it will be easier to deal with these points rather than a set of planes. So this is the concept. So reciprocal lattice to a direct lattice is constructed by the following. So we will describe now how this reciprocal lattice can be constructed. So what we have to do is take origin at some arbitrary point and draw normals to every set of parallel planes of the direct lattice. So in a lattice, we are choosing some arbitrary points as origin in some planes, and from this point of origin we are drawing normal to every set of parallel planes with length equal to reciprocal of the interplanar spacing. So each line from this origin will end up in some particular point. Okay, and take length of each normal equal to reciprocal of the interplanar spacing for the corresponding set of planes. The terminal points of these normals from the reciprocal lattice. So for example, consider a unit cell of monoclinic crystal in which A not equal to B not equal to C and alpha is equal to gamma is equal to 90 degree at beta greater than 90 degree as shown in figure. So this is a monoclinic crystal structure, and we are going to construct a reciprocal lattice corresponding to this monoclinic structure. So for simplicity, what we are doing is we orient the unit cell in such a way that B axis is perpendicular to the plane of the paper. So these are planes corresponding to 1, 0, 0, and this corresponds to, so this is A axis, this is C axis, and B axis is perpendicular to this. So we are representing these planes by these lines. Okay, these lines. So these are representing these planes, and this represents these planes. Okay, and what we are doing is we are choosing an arbitrary origin here, and we are drawing normal to each set of points. So what we are doing is we will for this these are parallel planes. Okay, these are parallel planes, and for this we are drawing normal to these planes. So we have chosen this point as origin, and we are drawing normal to these planes with length equal to reciprocal of the length of this interplanar distance. So this will end up here. So this is the end point, and again there may have a set of parallel planes here. So again we are drawing another line, and we will end up with n here and here and so on. Similarly, for this set of planes, what we will get, this is the normal direction, and in the normal direction we will get a spacing. This is the interplanar distance, and the reciprocal of this will end up with this point, and we will get this point, and the next point will be here and here and so on. So what we will get is we will get an array of points arranged in order just as in the crystal structure, and this will represent the reciprocal lattice of this monoclinic crystal. So this is, so instead of but in actual case we will get a set of parallel planes in this direction and in this direction, but instead in the reciprocal concept, corresponding to set of parallel planes, we will get lattice points in this reciprocal structure. So that's how this system simplifies the original crystal structures, and that's why this idea came here. So this is how a lattice, a reciprocal lattice is constructed. I will give you an animation video for the construction of the reciprocal lattice, then it will be easier for you to understand. Okay. So this is explained here how this reciprocal lattice is constructed. So this is the reciprocal lattice concept. Now we will define reciprocal lattice vectors. So reciprocal lattice vectors, which is represented by sigma suffix HKL, where HKL are Miller indices, is defined as a vector having magnitude equal to the reciprocal of the interplanar spacing DHKL and direction coinciding with the normal to the HKL planes. So we know this length of this vector will be the reciprocal of the interplanar spacing. So it can be defined as sigma HKL as 1 by DHKL, where DHKL is the interplanar distance and n cap, where n cap is the unit vector in the direction of normal to the HKL planes. In fact, a vector drawn from the origin to any point in the reciprocal lattice is a reciprocal lattice. So a vector drawn from the origin to any point in the reciprocal lattice is a reciprocal lattice vector. So like a direct lattice, a reciprocal lattice also has a unit cell which is of the form of parallelepiped. The unit cell is formed by the shortest normals along the three direction, that is along the normals to the planes 1, 0, 0, 0, 1, 0 and 0, 0, 1. So this unit cell definition is just as in the original crystal lattice. So this is the smallest cell or the shortest volume cell in the reciprocal lattice. These normals produce reciprocal lattice vectors designated as sigma 1, 0, 0, sigma 0, 1, 0 and sigma 0, 0, 0, 1, which represents the fundamental reciprocal lattice vectors. So for the reciprocal lattice vectors corresponding to the unit cell can be represented by these sigma 1, 0, 0, sigma 0, 1, 0 and sigma 0, 0, 1. So which are known as the fundamental reciprocal lattice vectors, which constitute the unit cell. Now let A, B and C be the primitive translation vectors of a direct lattice. So if we are considering a direct lattice space and A, B, C are the primitive translation vectors of this lattice, then the base of the unit cell is formed by the vectors B and C, and its height is equal to D100. So the base of this unit cell is formed by vectors B and C, just as we shown in the previous figure, and its height is equal to D100 means the interplanar spacing between this B and C vector. By considering as primitive lattice space B and C, so this will be the interplanar or interplanar spacing or height between these two planes. The volume of this cell V is equal to area into this height, area of this cell and the height of this planes. So what we will get? 1 by or from this equation we will get 1 by D100 as area by V. So the area can be represented as B cross C for sides B and C. So we will get B cross C, and divided by V. And what will be the volume? We can determine in vector form. The 1 by d00 can be represented as 1 by d00 n cap is equal to b cross c by v, where n is the unit vector normal to 100 planes. So we have got a vector in the vector form, the reciprocal lattice vector. So 1 by d100 means this is the reciprocal lattice vector, and which is the n is the direction. So from this equation we have represented sigma 100 as 1 by d100 n cap, which is this. And similarly for the reciprocal lattice vector corresponding to other planes 0, 1, 0, 0, 0, 1 are can be represented by this. So the axis will change according to the orientation of the plane. So here it is b cross c, and here it is c cross n, here it is a cross b, considering the sides of the unit cell. Now, denoting the fundamental reciprocal vectors sigma 100, sigma 0, 1, 0 and sigma 0, 0, 1 by a star, b star and c star respectively, and a dot b cross c as b dot c cross a, which is equal to c dot a cross b, is the volume of the direct cell. Then we can read that is in the original lattice the vectors are represented by a, b and c. So in the reciprocal lattice system we are representing the vectors as a star, b star and c star in order to recognize these two vectors, these two types of vectors. And the volume of the original lattice unit cell is a dot b cross c, which is equal to b dot c cross a, and again equal to c dot a cross b, that we know. So that this these fundamental unit vectors of this reciprocal unit cell, which is sigma 100, sigma 010 and sigma 001 can be represented as this is a star, which is b cross c divided by volume, which is b cross c divided by a dot b cross c, and the second vector sigma 010 as b star, which is c cross a divided by volume a dot b cross c, and again c star, which is sigma 001 as a cross b by a dot b cross c. Thus the reciprocal translation vectors bears a simple relationship to the crystal translation vector, as a star is normal to b and c, b star is normal to c and a, and c star is a normal to a, and this is quite clear from this expression. Since this is b cross c, then this vector is normal to both b and c. Similarly, b star is normal to both c and a, and so on. So this is a relationship between this original translational vectors and crystal reciprocal lattice vectors. In vector notation, this relation means a dot b and a dot c is equal to 0. Similarly, b dot c and b dot a is equal to 0, and c dot a and c dot b is equal to 0. So if you are taking scalar product of a star, b star and c star with a, b and c respectively, then from this expression, what we will get? What we are doing is we are taking scalar product with a dot a star, b dot b star and c dot c star. So we will get a dot b cross c and b dot c cross a and c dot a cross b. So in three cases the numerator and denominator will be equal, and the result will be 1. So we will get A dot A is equal to B dot B is equal to C dot C equal to 1. Okay. So from this expression, it is clear that A star, B star and C star are parallel to A, B, C respectively. That's why this relation, that is A dot A star, B dot B star and C dot C star came to 1. However, this is not always true. In non-cubic crystal systems such as monoclinic crystal system, as in previous figure, A star and A point in different directions, that is along OA prime and OA respectively. So this is shown here. This is OA and this is OA prime. So A is pointing this direction, A star pointing in this direction. So in monoclinic crystals, this A and A star is pointing in different directions. This all that is in equation 6 means that the length of A star is the reciprocal of A cos theta, where theta is the angle between A star and A. So what we have made the conclusion from the relation A star dot A is equal to 1 and B star B is equal to 1 and C star C is equal to 1 is that they are always parallel to each other. But it may not be always true. That's what we are describing here. In monoclinic structure, they are not parallel but orienting in different direction. That means, what does this mean is that the length of A star is the reciprocal of A cos theta. Then it will be reciprocal. A star is reciprocal of A cos theta. Then A star A will be 1. Theta is the angle between A star and O. So this possibility is also existing. So this is the right conclusion from these relations. So in some textbooks, the primitive translation vectors A, B and C of a direct lattice are related to the primitive translation vectors A star, B star, C star of the reciprocal lattice as A dot A star or B star B and C star C as 2 pi instead of 1. Okay, this equation can be satisfied by choosing the reciprocal lattice vectors as A star is equal to 2 pi into B cross C by A dot B cross C. That is an additional 2 pi is appearing here as coefficient of this reciprocal lattice vector. So some textbooks are describing these vectors in such a manner. Okay. So every crystal structure is associated with two important lattices, the direct lattices and the reciprocal lattice. The two lattices are related each other by the previous equation. The fundamental translation vectors of the crystal lattice and the reciprocal lattice have dimensions of length. Since these are vectors, this will have dimensions of length, and in the original lattice space and in the reciprocal lattice vectors, it will have a dimension of length inverse since it is the reciprocal lattice vector. This is why the reciprocal lattice vector is called, this is why it is called a reciprocal lattice. Also, the volume of the unit cell of reciprocal lattice is inversely proportional to the volume of the unit cell of a direct lattice. A crystal lattice is a real or ordinary space, that is the space defined by the coordinates, whereas the reciprocal lattice is a lattice in the reciprocal space associated K space or Fourier space. A wave vector K is always drawn in the K space. The reciprocal lattice space is a K space or Fourier space of the original lattice space. The points of the crystal's lattice is given by T is equal to MA plus NB plus PC. So any translation vector in a lattice space can be represented by, in the original lattice space can be represented by MA plus NB plus PC, where M, N and P are integers. Similarly, the same can be represented in reciprocal lattice vectors as G, which is HA star, KB star plus LC star, where HKL are integers, similar to this translation vector expression. So every point in the Fourier space has a meaning, but the reciprocal lattice is defined by this equation carry a special importance. What it is? In order to find the importance of G's, we take the dot product of G and T. So what we are doing is, we are taking the dot product of this G vector and T vector. This is corresponds to reciprocal lattice and this corresponds to the original lattice. So if we are taking the dot product of these two vectors, what we will get is, we will end up with, so we have used here the relation which includes 2 pi. So A star is 2 pi into B cross C by A dot B cross C, and here a coefficient H appears, and similarly K here, L here, and this another vector, and we will end up with 2 pi into HM plus KN plus LP. This is equal to 2 pi times n integers. So because these are integers, sum of integers, so this will represent an integer. Or what does this mean? Exponential of G dot T is equal to 1. This, it is clear from this expression that H, K and L define the coordinates of the points of reciprocal lattice space. In other words, it means that a point HKL in the reciprocal space corresponds to the set of parallel planes having the Miller indices HKL. The concept of reciprocal lattice is useful for redefining the Bragg's condition and introducing the concept of Brillouin zones. So this is so it is clear from these expressions that the coordinates corresponds to the reciprocal lattice. That's why this relation is ends up with a quantity unity. That's why the product of this will end up as unity. So it is clear that this is correspond to a reciprocal lattice vector. So this is about the concept of reciprocal lattice and how it is constructed and its importance in the crystal systems.